Southern Michigan, March 5, 2026. An EF3 tornado, 170 miles per hour. No meaningful forecast, no historical precedent for a storm this strong, this early, this far north. Homes flattened, people killed, 100,000 without power, and within days, a second potentially more dangerous system already forming over 36 million people. Scientists are not describing this as a random extreme event. They are describing it as evidence of something systematic, something directional, something that is accelerating. If you have ever looked at a tornado risk map and felt relief because your town wasn't on it, stay until the end. The map is being redrawn. If this has you hooked, subscribe to the Skylab, because as severe weather seasons grow longer and the Tornado Alley boundaries rewritten on the map, we will be here tracking all of it. Drop a comment telling me where you're watching from, and tell me honestly, do you think this storm is a one-time anomaly, or do you think the atmosphere is changing the rules? Now, let's get into it. Part 1, the EF3 that came from nowhere. Something tore through southern Michigan on the night of March 5th, 2026, and it was not supposed to be there. Not in March, not in Michigan, not with winds reaching 170 miles per hour. But there it was, grinding across Branch County, St. Joseph County and Cass County like nature had decided the rules no longer applied. Homes that had stood for decades were reduced to foundation slabs in seconds. Roofs were peeled off structures the way you'd peel the lid off a tin can. Power lines snapped and fell in cascades of sparks across roads that had become rivers of debris. And in the darkness and the chaos, people died. At least 8 people were killed across the broader outbreak. 4 of those deaths occurred in Michigan alone. More than 30 people were injured, many of them trapped beneath the collapsed wreckage of houses they thought were safe. Over 100,000 customers lost power across multiple states as the storm system continued its northeast march through the night. Union City High School, suddenly transformed from a place where teenagers take algebra tests into a full emergency relief hub, became the central nervous system of a rescue operation that no one had prepared for. Here is the number that stops meteorologists cold when they say it out loud. The winds inside that tornado were estimated between 145 and 170 miles per hour. That places it firmly in the EF3 category on the enhanced Fujita scale, which is the scale used to measure tornado intensity based on the damage it leaves behind. EF3 tornadoes are not rare in the United States taken as a whole, but in Michigan, meteorologists are describing this as one of the strongest tornadoes to strike that state in roughly 50 years, half a century. Think about how much the world has changed in 50 years, and then consider that the last time Michigan saw a tornado anywhere near this powerful disco was still on the radio. The enhanced Fujita scale runs from 0 to 5. Most tornadoes that touch down in any given year sit at EF0 or EF1. They snap branches, knock over fences, maybe tear off a section of roof. An EF3 is a different species of storm entirely. At those wind speeds, well-constructed homes are destroyed, cars are thrown considerable distances, trees are debarked by the wind, stripped down to pale naked wood like something out of a nightmare. This was not a minor weather event that got upgraded in the news cycle. This was a genuinely violent tornado doing exactly the kind of damage that violent tornadoes do, in a place that has almost no historical experience with violent tornadoes. And here is where it starts to get strange, even by the standards of a violent tornado tearing through southwestern Michigan in the middle of the night. The storm struck in early March, not April, not May, not June, when the atmosphere is fully loaded with summer heat and Gulf moisture, and the classic ingredients that produce the tornado outbreaks most people associate with the word tornado season. Early March is, historically speaking, not tornado season in Michigan. It is barely tornado season anywhere in the northern tier of the United States. The ground is still cold, the atmosphere is still transitioning out of winter. The conditions that breed the most violent rotating thunderstorms are not supposed to be available yet. And yet there the tornado was, doing 170 miles per hour, in March. In the immediate aftermath, as emergency crews work through the debris and families try to account for missing neighbours, meteorologists began asking a question that goes well beyond this one terrible night. If tornadoes like this are now possible in Michigan in early March, how many other places are now inside a risk zone that they don't know about? How many cities, How many towns, how many neighborhoods full of houses built to historical standards are now sitting in the path of a threat that has quietly migrated toward them while they were looking somewhere else? That is the question underneath this story. Not just what happened on the night of March 5th in southern Michigan, but what it means that it happened at all. Because the meteorologists who study tornado climatology, who spend their careers tracking where these storms occur and when and why, are not waving this event away as a fluke. They are not reassuring the public that this was just one of those random things that nature occasionally does. They are doing something more unsettling than that. They are saying they've been watching a pattern develop, and that this storm fits it almost perfectly. But before we get to the pattern, we need to talk about something that in some ways is almost as alarming as the tornado itself. Because the tornado did not just arrive without warning in a geographic sense. It arrived without warning in every sense. The forecast didn't see it coming, the models didn't see it coming, and the implications of that failure go far beyond one storm on one night in one corner of Michigan. Because if the forecast missed this one, the question you should be asking yourself right now is, what else are they missing? Part 2. The forecast gap that has meteorologists uneasy. The National Weather Service exists in its most fundamental purpose to give people time to move to a basement, time to pull over and shelter, time to make a phone call to someone you love and tell them to get inside. Warning time is the difference between a tornado that kills dozens and a tornado that kills hundreds, and the entire infrastructure of American severe weather forecasting is built around the singular goal of maximizing that window between the moment forecasters see danger coming and the moment danger arrives. In the days before the March 2026 outbreak, that window was almost non-existent. The Storm Prediction Center, which is the branch of the National Weather Service, responsible for issuing severe thunderstorm and tornado watches across the country, had placed the affected region under only a marginal severe weather risk in the lead-up to the event. Marginal. That is the lowest meaningful threat level on their scale. It means, yes, some bad weather is possible, but don't clear your schedule. Forecasters expected isolated thunderstorms. They expected the kind of weather that makes you grab an umbrella, not the kind of weather that makes you grab your children and run for the lowest point in your house. The models used by the National Weather Service rely on a combination of observational data and atmospheric physics to project what the atmosphere will do hours and days into the future. The primary tools in their arsenal include the GFS, which stands for Global Forecast System, the NAM or North American Mesoscale model, and the HRRR, the High Resolution Rapid Refresh model. These are enormously sophisticated pieces of computational science. They ingest billions of data points from weather balloons, satellites, aircraft, and surface stations, and attempt to simulate the behavior of the entire atmosphere at once. They are by any reasonable measure technological marvels, and they missed this storm. The atmosphere intensified faster than the models predicted. Instability developed more rapidly and more aggressively than the grid-based projections captured. By the time radar showed the signatures of supercell rotation forming, the lead time available to forecasters had collapsed to minutes rather than hours. Several meteorologists who reviewed the event afterward used a phrase that sounds almost poetic in its precision. They described what happened as rapidly evolving mesoscale chaos. Mesoscale refers to weather phenomena that operate at the intermediate scale, larger than a single thunderstorm cell, but smaller than the broad weather systems that dominate a regional forecast. Mesoscale convective processes are the tricky zone of atmospheric science, where things happen fast enough and at a scale small enough that the models sometimes simply don't see them coming. When a mesoscale feature develops rapidly inside an already unstable environment, the resulting escalation can be explosive in the most literal meteorological sense. Think of it this way. Weather prediction models work on a grid. Every grid square has an average value for temperature, moisture, pressure, and other variables. But the atmosphere doesn't operate on a grid. It operates continuously in 3 dimensions, with features that can be smaller than any grid square and still capable of triggering a violent supercell. When those small-scale features align in an unstable environment, they can catalyze an outbreak before the model even registers that something significant is happening. This is not a new problem. Meteorologists have known for years that mesoscale convective events can outpace model resolution, but the March 2026 storm put that abstract limitation in front of the public in the most concrete possible terms. 8 people dead, hundreds of homes destroyed, and a warning system that simply could not move fast enough. The public safety implications here are deeply uncomfortable. If storms can develop and intensify faster than warning systems can respond, then the traditional safety math changes. Instead of having 20 or 30 minutes of warning time to shelter, communities may have 5 minutes, or 2, or none. And in a world where more people than ever live in suburban and exurban communities far from traditional storm shelters, 2 minutes is not enough time. There is active work happening to close this gap. AI-assisted forecasting tools, improved satellite technology, and denser radar networks are all part of an ongoing effort to shrink the window between storm formation and warning issuance. We will get to that part of the story later because it is genuinely hopeful. But the gap exists right now, today, and the Michigan outbreak exposed it in a way that is difficult to look away from. And here's the thing that should really be keeping atmospheric scientists up at night. The models didn't just fail to predict one rogue storm, they failed in a region that was already transitioning into a historically unusual threat environment. Because Michigan, as it turns out, was not supposed to be in the path of anything like this at all. So why was it? Part 3. Michigan is not Tornado Alley, or wasn't. Every American schoolchild learns the same mental map of tornado risk. The great diagonal swath of the Great Plains, running from North Texas up through Oklahoma, Kansas, and Nebraska, painted in perpetual red and orange on every severe weather graphic you've ever seen. Tornado Alley. The place where Dorothy got swept away, where storm chasers in pickup trucks spend their springs driving toward rotating clouds that most sensible people drive away from. That is where tornadoes happen. That is the deal. Michigan was not part of that deal. Michigan's historical tornado record is not empty. Tornadoes do occur in the state, but the overwhelming majority of those tornadoes sit at EF0 or EF1 on the intensity scale. They break trees, they damage outbuildings, they occasionally tear off a section of roof or shatter windows. They are genuinely dangerous, and people have been hurt and killed by them. But they are not the kind of storm that demolishes an entire neighborhood in the time it takes to run from one room to another. EF3 tornadoes represent a small fraction of all tornado events nationwide in any given year. Most tornadoes that touch down anywhere in the country are relatively weak. The violent tornadoes, EF3 and above, account for a disproportionate share of tornado fatalities, even though they constitute a small percentage of tornado events. They are the tail of the distribution that does most of the killing, and for Michigan, that tail was historically so thin as to be almost theoretical. The Union City tornado changed that math in one night. There is a vulnerability issue that emerges from this history that is worth sitting with for a moment. Regions that have historically experienced low tornado risk are built accordingly. Housing construction in Michigan reflects decades of relatively modest tornado exposure. Homes are wood frame, which is the standard American construction method, but they are not built with the additional reinforcement measures that increasingly appear in parts of Oklahoma and Kansas, where residents have lived with severe tornado risk for generations. Basement penetration rates, which is simply the percentage of homes that have a below-ground shelter option, tend to be higher in high-risk areas and lower in historically low-risk areas. This creates a compounding problem. If tornado risk is migrating into regions that were historically safe, those regions are populated with homes that aren't designed to resist the new threat level, and with residents who haven't grown up with the ingrained cultural habits of tornado preparedness. In traditional Tornado Alley, a certain proportion of people will automatically move toward a basement or interior room when sirens go off, because they've done it since childhood. In Michigan, in Tennessee, in Indiana, that reflexive response is less developed. The cultural infrastructure of tornado safety takes generations to build, and the atmosphere may not be giving these communities that much time. Researchers studying severe weather trends have been documenting increasing activity in what some are beginning to call a Dixie Alley to Midwest corridor, a zone that arcs from the deep south northward through Tennessee, Kentucky, Illinois, Indiana, and increasingly into Michigan. This is not a fringe observation. Multiple peer-reviewed studies have examined the apparent eastward and northward shift in tornado activity over recent decades, and while the science includes genuine debate about causes and magnitude, the directional signal in the data has been consistent enough to generate serious concern among researchers who study it full-time. One of the additional dangers in these new risk zones is purely geographical. Tornado Alley on the Great Plains is relatively flat and open. You can often see a tornado coming from miles away. You can watch its path and make reasonable judgments about your safety window. The Midwest and Southeast are different terrain entirely. Trees, hills, and rolling geography can hide a tornado until it is extremely close. Visibility is reduced. The atmospheric warning you get from watching a dark sky approach from the west is compressed into seconds rather than minutes. So the storm that hit Michigan was unusual in its intensity. It was unusual in its timing. It struck a region with historically low exposure to this threat level, and it arrived faster than the forecast system could communicate danger. Any one of those factors alone would be noteworthy. All four together start to look like something more than coincidence. But why did the atmosphere have enough energy to produce an EF3 tornado in Michigan in early March to begin with? What was going on up in the sky that night that made something this violent possible? Part 4. The atmosphere that was overclocked. To understand how a tornado forms, you need to understand what the atmosphere is doing in the hours and days before a supercell develops. Because a violent tornado doesn't just appear, it is assembled piece by piece by atmospheric conditions that have to align with a kind of terrible precision. 3 ingredients are required at minimum, and the March 2026 system had all 3 of them running at levels that would have been remarkable even in peak tornado season. The first ingredient is instability. The atmosphere becomes unstable when warm air sits near the surface, beneath cooler air at higher altitudes. Warm air wants to rise. Cool air above it resists that rise up to a point, and then, when the trigger comes, the warm air erupts upward like a fast-forwarded volcanic plume. The measure of this instability that meteorologists use most often is called CAPE, which stands for Convective Available Potential Energy. CAPE is expressed in joules per kilogram, and it is essentially a measure of how much energy is available to a rising parcel of air. The higher the CAPE, the more violently the atmosphere will explode when it finally releases. On the day of the outbreak, CAPE values in the affected region were forecast near 3,500 joules per kilogram. For context, most significant tornado outbreaks occur in environments with CAPE values between 1,500 and 2,500 joules per kilogram. 3,500 is exceptional under any circumstances. In early March, when the atmosphere is traditionally still cold and relatively quiet, 3,500 joules per kilogram is, as one meteorologist put it, not supposed to be there. That is a May number. That's a number you see in the peak of severe weather season, when the atmosphere is fully loaded with summer warm Gulf air and maximum solar heating. The second ingredient is moisture, specifically deep atmospheric moisture originating from the Gulf of Mexico, which is the primary supplier of the humid air that fuels American thunderstorms. In the days before the outbreak, a massive warm sector developed that stretched from the Gulf all the way north to the Great Lakes region. Warm, moist air surged northward at a rate, and to a latitude that was highly anomalous for early March. The low-level jet stream, which is essentially a river of wind in the lower atmosphere that transports warm Gulf air northward overnight, was running particularly strong. Dew points across the region climbed into ranges more typical of late spring or early summer. This moisture is the fuel. It is the chemical energy in the tank before the spark. The third ingredient is wind shear. Wind shear refers to changes in wind speed and direction with altitude. When the wind near the surface blows from the south or southeast, while winds higher in the atmosphere blow from the west or southwest, you get a rotation effect. A horizontal tube of spinning air gets tilted vertical by a rising thunderstorm updraft, and when that happens inside an environment with very high CAPE and abundant moisture, you get a supercell. A supercell is a rotating thunderstorm, an organised, long-lived convective system with a persistent rotating updraft called a mesocyclone. Supercells are the storms that produce the large, long-track tornadoes. They are the predators of the atmospheric world. On the night of March 5th, forecasters described the atmospheric environment as, quote, loaded with fuel. Cold air descending from Canada collided along a sharp boundary with warm, moist Gulf air that had surged unusually far north. That boundary became a focal point for storm initiation. When the storms finally fired, they had an enormous reservoir of energy to draw from, and they grew fast. This is the part where a useful metaphor helps. Imagine filling a pressure cooker with more and more steam, well past the level it was designed to handle, with the lid locked on. The energy inside keeps building, and building. And then, when the seal finally breaks, everything that was being held back releases at once. That is what a high CAPE, high shear atmospheric environment does. It stores tremendous energy under a layer of stable air called a cap, and when the cap breaks, the release is sudden, violent, and difficult to predict with precision. The March 2026 atmosphere was not just loaded. It was, in the language of the meteorologists who reviewed it afterward, overloaded for the season, running hot in a way that shouldn't have been possible in March. And here is the part of the story that should make you set down whatever you're doing and pay attention, because the atmosphere wasn't done. Part 5. The storm was only the first shot. Meteorologists have a phrase for a certain kind of atmospheric setup. They call it a loaded gun. A loaded gun atmosphere is one where all the ingredients for a violent storm outbreak are in place, cocked and ready, waiting only for the trigger. The March 2026 outbreak was a loaded gun. But even as rescue workers were still pulling people from the rubble in Michigan, the atmosphere was loading another one. In the days following the initial outbreak, forecast models began tracking a second powerful storm system developing over the central United States, and the numbers coming out of the models were, depending on your relationship with severe weather, either fascinating or deeply frightening. Record early season temperatures were being forecast near 80 degrees Fahrenheit across parts of Illinois in March. Dew points in the lower 70s, which is an extraordinary moisture value for any time of year in the Midwest, let alone in early spring. Cape values projected to exceed 3,000 joules per kilogram again. Over 36 million people were being placed under severe weather risk zones as the models refined their projections. 36 million people. That is roughly the population of California. The setup for the second system bore the hallmarks of what atmospheric scientists call a classic loaded gun scenario. A strong cap sitting atop a deeply unstable and moisture-laden air mass. The cap prevents storms from firing prematurely. It traps the heat and the moisture beneath it, letting the pressure build hour after hour. Then, in the afternoon when surface heating is at its maximum, and a trigger like a cold front or a dry line arrives, the cap breaks. And when a cap breaks over an environment with 3,000 plus joules per kilogram of cape and strong wind shear, the storms that develop are not ordinary thunderstorms, they are supercells, and they can produce long-track tornadoes, which are the most dangerous kind, tornadoes that stay on the ground for tens or even hundreds of miles, carving a path of destruction that can cross multiple counties before the circulation finally weakens and the funnel retreats back into the cloud. Some of the meteorologists tracking the second system were using language that, coming from people trained in careful scientific caution, should be understood as an alarm. Words like potentially more dangerous than the first system. Phrases like maximum atmospheric instability for the season so far. The second outbreak had not yet occurred as forecasters analysed it, but the atmospheric ingredients were assembling in a way that matched some of the most significant severe weather outbreaks in recent memory. Two violent severe weather setups, within days of each other, in early March, at atmospheric energy levels more consistent with the height of tornado season than with the early transition out of winter. And at least one of them, the Michigan outbreak, striking a region with no cultural or structural preparation for this threat level, producing an EF3 tornado that wasn't in the forecast and wasn't supposed to be geographically possible. At some point, you have to stop calling something an anomaly and start asking whether it's a trend. Meteorologists who study tornado climatology have been asking that question for years, and the answer they've been assembling piece by piece from historical data and climate analysis and atmospheric modelling is more unsettling than most people outside the field have been told. Because Tornado Alley, it turns out, is moving. And it's moving toward places that aren't ready for it. Part 6. The migration of Tornado Alley. The idea of Tornado Alley as a fixed geographic feature, a permanent stripe of the map where tornadoes happen, and outside of which they mostly don't, has been a comfortable organising principle for American severe weather awareness for decades. It gave people a sense that tornado risk had an address, that it lived somewhere specific, that the residents of that somewhere specific had accepted a certain atmospheric bargain in exchange for flat land and wide skies, and whatever else the Great Plains offers. That bargain appears to be renegotiating itself. Researchers analysing tornado occurrence data over recent decades have documented a pattern that is statistically meaningful and geographically coherent. Tornado frequency in the traditional core of Tornado Alley, the parts of Texas, Oklahoma, Kansas, and Nebraska, where the risk was historically highest, has shown a modest but measurable decline. Meanwhile, tornado activity in states to the east and north has shown an increase. Tennessee, Kentucky, Illinois, Indiana, Michigan. These states are recording more severe tornado events than their historical baselines would predict, and the trend line points in a consistent direction. The phenomenon has acquired a working name in the research community, the eastward shift of tornado activity. Some researchers fold it into a broader concept of expanding tornado risk zones, acknowledging that the shift appears to be both eastward and, in some analyses, northward as well. The March 2026 Michigan event fits this pattern with uncomfortable precision. An EF3 tornado in a state that historically saw almost no tornadoes of that intensity, arriving early in the calendar year with atmospheric conditions more typical of peak season. If you were designing a case study to illustrate the eastward shift, you might build something that looks exactly like what happened in Union City. The possible drivers of this shift are multiple and interconnected in ways that make the science genuinely complex. Changes in atmospheric circulation patterns, particularly in the behavior of the jet stream, appear to be playing a role. The jet stream is the high-altitude river of wind that largely governs weather patterns across North America, and it has been behaving with increasing variability in recent years. When the jet stream dips further south or oscillates more dramatically, it can push the boundary between warm southern air and cold northern air into different geographic locations, shifting where the prime tornado breeding grounds sit. Warmer temperatures at the surface, driven by the broader warming trend in the climate system, are affecting the geographic reach of the moisture plumes that fuel severe weather. The Gulf of Mexico is warmer than it was 50 years ago. Warmer water evaporates more moisture. That moisture gets carried further north before it cools sufficiently to lose its energy-supplying properties. The result is that the zone of maximum atmospheric instability, the zone where CAPE values reach their peak during severe weather setups, is expanding its northern and eastern boundaries. Here is where the science gets genuinely contested, and intellectual honesty requires acknowledging the debate directly. Some researchers argue that the apparent increase in tornado activity in non-traditional regions may partly reflect improvements in detection technology, rather than a real change in storm frequency. Doppler radar networks have expanded dramatically over the past 30 years. Population growth in rural areas means more eyes on the sky. Storm reporting has improved. It is possible that some of what looks like an increase in tornado activity in the eastern states is actually an increase in our ability to detect and report events that were always happening, but going unnoticed. That debate is real, and it is ongoing, but the researchers who argue for a genuine atmospheric shift point to the intensity of events like the Michigan tornado as evidence that detection improvements alone cannot explain what they're observing. You cannot fail to detect an EF3 tornado. The damage it leaves behind is not subtle, and the atmospheric ingredients that produced the March 2026 outbreak, the extraordinary CAPE values, the anomalous moisture depths, the timing in early March, those are not a detection artifact. Those are measured data. The migration of tornado risk, if it is real and if it is continuing, has consequences that extend far beyond the meteorology. And a lot of those consequences start with a body of water sitting several hundred miles to the south of Michigan that has been quietly changing the math of American severe weather for decades. Part 7. The Gulf of Mexico is supercharging storms. The Gulf of Mexico does not get enough attention in popular discussions of American weather. People think about it in the context of hurricanes, which is reasonable, because it absolutely does serve as the incubator for a significant portion of Atlantic hurricane activity. But the Gulf's influence on American weather extends far beyond the hurricane season, and in the context of severe weather across the interior of the country, it may be the single most important geographic feature on the continent. Here is the basic mechanism. The Gulf sits south of the main body of the United States, relatively shallow in its northern reaches, and extraordinarily warm by the standards of a body of water at that latitude. Water evaporates from its surface continuously, loading the lower atmosphere with heat and moisture. That moisture doesn't stay over the Gulf. It gets transported northward by the wind patterns of the lower atmosphere, and the primary vehicle for this transport is a feature called the low-level jet stream. The low-level jet stream is different from the polar jet stream that most people are familiar with. It operates in the lower part of the atmosphere, typically between 1,000 and 5,000 feet above the ground, and it flows predominantly from south to north overnight, drawing Gulf air deep into the interior of the continent. The low-level jet is the pipeline that delivers atmospheric fuel to the central and eastern United States, and it is particularly active in the spring months when the temperature contrast between the warming land surface and the still cool air to the north is at its maximum. Recent observations show that Gulf water temperatures have been running above historical averages. Warmer water means more evaporation. More evaporation means more moisture loading in the lowest levels of the atmosphere. More moisture in the low levels means higher Cape values when the atmosphere eventually becomes unstable. Higher Cape values mean more energetic convection when the trigger finally arrives. This is a cascade of amplification, each step feeding the next, and it plays out across a chain of causality that connects a slightly warmer patch of water in the northern Gulf to a rotating supercell over Michigan. The timing dimension matters enormously here. When Gulf moisture is delivered further north and earlier in the year than historical patterns suggest it should be, it arrives in environments that are not yet seasonally prepared for it. The jet stream is in a transitional configuration. Atmospheric circulation patterns are shifting between their winter and spring modes. When anomalously warm, moist air intrudes into those transitional patterns, it can interact with cold air masses that are still present from winter in ways that generate extreme instability, sometimes faster and more violently than in the more predictable peak season setups. Some meteorologists studying long-term severe weather trends have concluded that severe weather seasons are effectively starting earlier in the calendar year than they did 2 or 3 decades ago. The first significant tornado outbreak of the year is arriving earlier. The last significant outbreak is arriving later. The window of peak atmospheric risk is widening at both ends. The Michigan tornado sits perfectly within this emerging pattern. An early March EF3 produced by a Gulf moisture plume that arrived weeks ahead of historical schedule, interacting with atmospheric instability that shouldn't have been available yet. The Gulf of Mexico, in other words, is essentially providing more fuel for longer periods of the year, and that fuel is now reaching further into the continental interior than it historically did. The storms that result from this arrangement are not fundamentally different in their physics from the storms that have always crossed the plains. They are the same machinery, driven by the same atmospheric dynamics, just operating with a bigger tank of gas, starting earlier in the season and arriving in places that weren't on the traditional itinerary. And when that fuel encounters a specific atmospheric configuration, something meteorologists call a loaded gun setup, the results can be extraordinary in the most dangerous possible sense of that word. Part 8. The loaded gun atmosphere. There is a concept in severe weather meteorology that captures, better than almost any other, the particular dread of watching a major tornado outbreak develop on forecast models hours before it arrives. Meteorologists call it the loaded gun atmosphere, and the name is almost too perfect. It describes exactly what it feels like to watch the atmospheric data come in and understand what is being assembled overhead. A loaded gun atmosphere requires a specific arrangement of ingredients that you've now heard about in pieces. You need high instability, the enormous CAPE values that measure how much energy is available for vertical atmospheric motion. You need deep moisture, the Gulf air carrying its fuel payload into the region. You need strong wind shear, the changing wind speed and direction with altitude that gives a developing thunderstorm its rotation. And you need one more thing: a cap. The cap is technically called a convective inhibition layer, and it is a critical part of the loaded gun setup. It is a layer of relatively stable, warm air sitting in the mid-levels of the atmosphere, above the moist and unstable surface air but below the colder air higher up. The cap prevents thunderstorms from firing prematurely. It acts like the lid on that pressure cooker, holding everything in while the energy continues to build. A strong cap over a deeply unstable atmosphere is not a safe situation. It is a dangerous situation on a delay timer. Throughout the day, solar heating at the surface continues to increase the instability beneath the cap. The low-level jet continues to stream moisture into the region overnight. Cape values climb, wind shear strengthens, and the cap holds. All that energy sits there, building, with nowhere to go. Forecasters watching this scenario develop feel the specific tension of knowing that the release, when it comes, will be explosive. The trigger that finally breaks the cap is usually a boundary of some kind, a cold front arriving from the west, a dry line, which is the boundary between moist and dry air masses that is a classic tornado trigger on the plains, a mesoscale convective boundary generated by outflow from earlier storms. When the trigger arrives and the cap breaks, storms don't develop gradually. They erupt, Convection fires in a matter of minutes, and if the cap has been holding energy long enough and the environment is sufficiently unstable, the first storms that develop may already be supercellular within 30 minutes of initiation. Supercells are the exception in the distribution of thunderstorms. They represent a small percentage of all convective events, but a dramatically disproportionate share of tornado production and of tornado fatalities. A supercell has a persistent, organised rotating updraft that can sustain itself for hours. This rotation is the mesocyclone, and when the mesocyclone tightens and descends toward the surface, a tornado may form. In a highly unstable environment with strong shear, a supercell's tornado may stay on the ground for a very long time and may intensify to EF3, EF4, or EF5 intensity. The March 2026 system showed strong signatures of the loaded gun pattern. The cap had been suppressing convection while moisture deepened and instability accumulated beneath it. When the trigger arrived, the storms that developed had an enormous reservoir of energy available to them. Tornado formation followed quickly, and because the environment was so unstable, the tornado that formed over southern Michigan was able to tap into that energy reservoir and intensify to EF3 intensity before it had travelled far enough for forecasters to issue meaningful lead-time warnings to residents in its path. Here is the part that the science of the loaded gun atmosphere makes unavoidably clear. The problem is not simply that this one storm developed faster than expected. The problem is that the size and charge of the gun is increasing. More fuel, earlier in the season, across a wider geographic area. Loaded gun setups are not becoming more common because meteorologists suddenly got better at identifying them. They are becoming more common because the atmospheric conditions required to produce them are becoming more readily available, and the structures that people are living in when those guns go off are almost entirely unprepared for what happens next. Part 9. The construction problem nobody talks about. 8 people died in the broader March 2026 outbreak. 4 of those deaths were in Michigan. Let's hold on that for a moment because embedded in that number is an engineering question that rarely makes the news, but sits at the centre of tornado fatality statistics in a way that is difficult to argue with. American homes are almost universally built from wood. Wood frame construction is the dominant residential building method in the United States and has been for more than a century. It is relatively inexpensive, widely understood by builders, adaptable to different architectural styles, and perfectly adequate for the vast majority of weather events that any given home will ever experience. For wind speeds up to roughly 90 or 100 miles per hour, a well-built wood frame house with a properly engineered roof will survive with repairable damage. At 145 to 170 miles per hour, which is the wind speed range of the Union City EF3 tornado, a well-built wood frame house does not survive. It is destroyed. The walls may remain standing in fragments, or they may be blown away entirely. The roof will be gone. The interior contents, furniture, appliances, personal possessions accumulated over a lifetime will be scattered across a debris field extending hundreds of yards in every direction. And any person inside that house who is not in the lowest possible interior location, ideally below grade, is at serious risk of injury or death. Here is the international comparison that structural engineers sometimes raise in discussions about tornado fatality rates. In many European countries, and in parts of Asia, residential construction defaults to masonry or reinforced concrete rather than wood framing. Stone walls, concrete block, structures built to withstand not just weather, but the physical forces of time itself. These structures do not perform the same way as wood frame homes in high winds. They are substantially harder to destroy. Walls that weigh tons per square foot require orders of magnitude more force to move than walls built from dimensional lumber. Under EF3 winds, a masonry or reinforced concrete structure may sustain heavy damage, but the structural shell is far more likely to remain standing and to protect the occupants inside. The engineering solutions exist. Tornado-resistant construction is not a theoretical proposition. Reinforced concrete dome homes, for instance, have survived direct EF5 tornado strikes with minimal structural damage. Monolithic concrete construction can be designed to withstand wind speeds far exceeding the most intense tornadoes ever recorded. The physics are not in question. The obstacle is cost. Reinforced concrete construction is significantly more expensive than wood framing, and in the American housing market, construction cost translates directly into housing affordability. Requiring all new residential construction to meet tornado-resistant standards would add thousands or tens of thousands of dollars to the cost of every new home built in affected regions. In an environment where housing affordability is already a significant political and economic issue, that conversation runs into structural resistance, and the punt is unavoidable almost immediately. There are intermediate solutions that engineers and building code advocates push for. Storm shelters, either standalone underground units or reinforced interior safe rooms built into standard wood frame homes, can provide life safety protection at a fraction of the cost of full tornado-resistant construction. Safe room programs have been federally subsidized in high-risk areas of traditional Tornado Alley, with measurable results in fatality reduction. As tornado risk migrates eastward and northward into regions that have historically not prioritized these programs, the question of how to extend tornado-safe infrastructure to new populations is becoming urgent. The Michigan tornado made that urgency visible. Homes in Union City were built to the standards appropriate for the risk level those communities had always been told they faced. That risk level turned out to be wrong, and the construction reflected the old understanding, not the new reality. The atmosphere is updating faster than the building codes. Part 10. Forecasting limits in a changing atmosphere. Weather prediction is one of the great scientific achievements of the 20th century. Genuinely, take a moment to appreciate it, because we rarely do. The ability to tell you, with reasonable accuracy, what the atmosphere over your specific location will be doing 5 days from now is an extraordinary thing. It rests on decades of accumulated research, computational development, and observational infrastructure that spans the entire globe. From weather balloons released twice daily at hundreds of stations worldwide, to satellites tracking moisture plumes over the open ocean, to a network of Doppler radar installations that together paint a near-continuous picture of what the atmosphere is doing over the continental United States at any given moment. The modern weather forecast is the product of thousands of scientists, tens of thousands of sensors, and some of the most powerful computers on Earth, all working in continuous coordinated collaboration toward a single goal, giving you time to make a decision before the weather makes it for you. And still, the March 2026 outbreak arrived with almost no warning. That sentence deserves to sit alone for a moment, because the gap between those two things, between the extraordinary sophistication of modern forecasting and the near-total failure to anticipate this particular outbreak, is not a small gap. It is not a rounding error or a minor miss that trained specialists can explain away with technical caveats. It is a fundamental illustration of where the limits of the current system are and why those limits matter enormously in a world where atmospheric conditions appear to be shifting in ways the models weren't designed to accommodate. Understanding the failure requires understanding how the models actually work at a fundamental level, which means we need to spend a moment on the architecture of modern weather prediction. The technical name for the computational approach used by the primary American forecast models, the GFS, which is the global forecast system, the NAM, which is the North American mesoscale model, and the HRRR, which is the high-resolution rapid refresh, is numerical weather prediction. The approach works by dividing the atmosphere into a three-dimensional grid and applying the equations of atmospheric physics to each grid cell, projecting how conditions in each cell will evolve over time based on its interactions with the cells around it. Temperature, pressure, moisture, wind speed, wind direction, these variables are tracked cell by cell, step by step, forward through time, generating the forecast you eventually see on your phone. The accuracy of the result depends on three things: the resolution of the grid, the quality of the initial conditions fed into the model at the start of the forecast, and the fidelity with which the physical equations capture what the real atmosphere actually does. All three of these factors have improved dramatically over the past 50 years. Grid resolutions have increased, observational networks have expanded, providing better initial conditions. The physical parameterizations, which are the mathematical approximations used to represent atmospheric processes that happen at scales too small to explicitly resolve, have been refined through decades of research. And yet the grid resolution remains the critical limitation, the one that cannot simply be engineered away. Even the highest resolution operational forecast models run on grids where each cell represents several kilometers of atmosphere. The HRRR, which is the most finely resolved operational model in routine American use, runs at a 3-kilometer horizontal grid spacing. 3 kilometers is genuinely impressive by the standards of even a decade ago. It is still enormous by the standards of the atmospheric features that can trigger a violent tornado outbreak. Atmospheric features smaller than the grid resolution are in a very real sense invisible to the model. They do not exist in the mathematical world the model is simulating. The model has no representation of them, no mechanism for their influence on larger scale conditions, no way of knowing they are there. Small-scale features, including the mesoscale boundaries and convective triggers that can initiate rapid tornado-producing storm development, may fall below the model's detection threshold entirely. When a tornado outbreak is driven by one of these subgrid scale initiators, the kind of subtle atmospheric boundary or small moisture gradient that can serve as the spark in an already loaded environment, the model literally cannot see it coming. It registers the explosive storm development only after it has already begun, at which point the warning-led time has collapsed from hours to minutes or less. This is what meteorologists mean when they describe the March 2026 event as rapidly evolving mesoscale chaos. The chaos was real, but it was also, in a specific technical sense, invisible to the tools being used to look for it. There is a second limitation that is in some ways more troubling than grid resolution, because grid resolution is at least a problem the community is actively solving through better computing power and model development. This second limitation involves the foundational assumptions built into the models themselves. Traditional numerical weather prediction is based on the equations of atmospheric physics, as they have been understood and parameterized over decades of observation and research. Those equations are correct, insofar as they accurately describe the atmosphere as it has historically behaved. They encode the statistical relationships between variables that have been measured and verified across many years of data. But here is the uncomfortable implication. If the atmosphere is undergoing systematic changes, if the statistical distributions of temperature, moisture, and energy that the models have been tuned to expect are shifting, then the models may be becoming progressively miscalibrated for the environments they are trying to predict. A model trained on historical climate conditions will perform best in conditions that closely resemble that history. When the atmosphere moves into configurations that have few strong historical analogues, when moisture arrives further north than it historically reached, when Cape values in early March exceed levels that were previously only observed in May, when the atmospheric energy budget looks more like a different season entirely, the model is operating in territory its training did not fully prepare it for. Its accuracy may degrade in ways that are genuinely difficult to anticipate in advance. Researchers and operational forecasters are acutely aware of both of these limitations and are actively working to address them on multiple fronts. Improvements in satellite observation technology are providing more detailed and more frequent measurements of atmospheric conditions, particularly in the data-sparse regions over the oceans, where many significant storm systems originate and where the initial conditions fed into forecast models have historically been weakest. Expanded and upgraded Doppler radar networks, including the ongoing modernization of the NEXRAD system that forms the backbone of American weather radar coverage, are improving the detection of storm-scale atmospheric features that were previously below the observational threshold. And perhaps most significantly, artificial intelligence and machine learning approaches are beginning to be applied to weather prediction in ways that are generating genuine excitement in the atmospheric science community. AI models like GraphCast, developed by Google DeepMind, and Pangu Weather, developed by Huawei researchers, have demonstrated forecast skill that matches, or in some evaluations exceeds, the traditional models, at a fraction of the computational cost and at speeds that open up possibilities for forecast updating that are simply not feasible with traditional numerical approaches. The potential for AI to detect atmospheric patterns that human forecasters and traditional models consistently miss, including the subtle precursor signatures of rapidly developing severe weather, is one of the most actively researched areas in the field right now. These developments are genuinely exciting. They represent the direction the science is moving, and the direction is a hopeful one. The combination of better observations feeding better initial conditions into better models running at higher resolutions and supplemented by AI pattern recognition tools represents a meaningful improvement in the warning capability that communities will eventually have access to. But the word eventually is doing heavy lifting in that sentence. These are, for the most part, works in progress. The tools exist in research environments and in early operational deployment, but the gap between what is possible in a research setting and what is operationally deployed in the warning systems that send alerts to people's phones is not trivial. It involves not just scientific development, but institutional adoption, operational testing, regulatory approval, and the slow process of building forecaster confidence in new methodologies. Neither the scientific development process nor the institutional implementation process moves quickly. Both move at the speed of careful, rigorous work, which is the right speed for science and an uncomfortable speed for communities that need better warnings now. What exists right now, today, in the operational warning system is a capability that performed inadequately for the Michigan outbreak. In a region where the atmospheric risk has apparently increased beyond what historical norms predicted, with a warning-led time that collapsed to minutes rather than hours, with a second, potentially worse outbreak already forming days later, over 36 million people. The question of whether the forecasting science can catch up to the pace of atmospheric change is one of the most consequential questions in applied meteorology right now, because the answer determines how much time people have to get to safety when the next loaded gun setup fires. And the next one, as the data keeps suggesting, may not wait for a convenient moment on the calendar to announce itself. Part 11. AI weather models are starting to beat traditional forecasting. Something unusual happened in the last 2 years that the meteorological community is still processing, and the word unusual is doing some serious understatement work in that sentence. A series of artificial intelligence weather prediction models, built not by the government weather agencies that have historically owned this domain, but by technology companies and university research institutions, began producing forecasts that matched, or in some cases outperformed, the established models that have been the backbone of global weather prediction for decades. In a field where incremental improvements are celebrated and major breakthroughs are measured in years, this was the equivalent of a newcomer walking into a chess grandmaster tournament and winning on the first try. The event that really focused attention happened in 2023. GraphCast, an AI weather prediction system developed by Google DeepMind, made headlines across the atmospheric science community when independent evaluations showed it producing more accurate 10-day forecasts than the ECMWF, the European Centre for Medium-Range Weather Forecasts. If you don't spend your days in meteorology, the significance of that comparison requires a brief explanation. The ECMWF, based in Reading, England, has been considered the gold standard of global weather prediction for decades. When American meteorologists want to compare their models against the best in the world, they compare against the ECMWF. When forecast verification studies are conducted, the ECMWF is typically the benchmark that everyone else is measured against. It is, in the language of competitive forecasting, the model you have to beat to prove you belong at the table. GraphCast beat it, and the meteorological community sat up very straight and paid attention. Pangu Weather, developed by researchers at Huawei, demonstrated similar capabilities in its own independent evaluations. ForecastNet, developed at the National Center for Atmospheric Research and NVIDIA, showed strong performance on medium-range forecasting tasks. Neural GCM, a hybrid system developed by Google Research, demonstrated the ability to simulate atmospheric dynamics with a combination of machine learning and physical equations that opened a new architectural direction for the field. Several other AI-based forecasting architectures followed in relatively rapid succession, each demonstrating predictive skill at levels that surprised even veteran atmospheric scientists who had spent careers building and refining the traditional models these newcomers were outperforming. To understand why this is such a significant development, you need to understand how these AI systems work and how fundamentally different their approach is from the numerical weather prediction models they are challenging. Traditional numerical weather prediction, as we discussed, works by dividing the atmosphere into a grid and applying the equations of atmospheric physics to each grid cell. Stepping forward through time mathematically, it is a physics simulation. It is an attempt to represent, as faithfully as computational resources allow, the actual physical processes that govern how the atmosphere behaves. Every forecast it produces is grounded in the same differential equations that describe fluid dynamics, thermodynamics, and radiation transfer that physicists have been refining for over a century. AI weather models do not simulate physics. They do something categorically different, and that difference is both their greatest strength and their most significant vulnerability. Rather than solving equations from first principles, AI weather models learn statistical patterns from enormous historical datasets, sometimes encompassing decades of global atmospheric observations at multiple vertical levels across the entire planet. They learn in effect what the atmosphere tends to do next, given a particular starting configuration. They are not asking the question that a physicist asks. Given these forces, what will the atmosphere be doing in 6 hours? They are asking a fundamentally different question. Given everything I have learned about how the atmosphere has behaved across thousands of previous cases, what does a starting configuration like this one tend to evolve into? This distinction sounds almost philosophical, but it has enormously practical consequences. The most immediately obvious consequence is speed. Running a global forecast on the ECMWF requires hours of computation time on some of the most powerful supercomputers on Earth, machines that occupy server halls the size of warehouses and consume electricity at rates that would power small cities. GraphCast can generate a comparable 10-day global forecast in roughly 1 minute on a single high-end graphics processing unit of the kind that fits inside a desktop computer. Read that again slowly. 1 minute on one GPU versus hours on a supercomputer. This is not a marginal efficiency improvement. It is a difference of multiple orders of magnitude in computational cost and time, and it opens up possibilities that are simply not feasible within the architecture of traditional numerical weather prediction. The possibility that most directly matters for the severe weather warning problem is ensemble forecasting at unprecedented scale and frequency. Ensemble forecasting is the practice of running multiple versions of a forecast simultaneously, each with slightly different initial conditions to generate a probabilistic picture of how the atmosphere might evolve across a range of possible scenarios. Ensemble systems are enormously valuable for communicating forecast uncertainty and for capturing the range of possible outcomes when the atmosphere is in a sensitive state. But they are computationally expensive. Running 50 ensemble members on a traditional model requires 50 times the computational resources of running a single deterministic forecast. With AI models that run in 1 minute on commodity hardware, you could theoretically run hundreds or thousands of ensemble members continuously, updating in near real time as new observational data arrives. For severe weather prediction specifically, the implications of this capability are significant in a way that connects directly to the Michigan outbreak. One of the fundamental limitations exposed by the March 2026 event was the time lag between atmospheric data collection, model execution, and forecast dissemination. The atmosphere was evolving faster than the warning system could process and communicate what it was seeing. An AI forecasting system capable of ingesting new radar and satellite data and regenerating a full probabilistic severe weather forecast every few minutes rather than every hour or few hours could dramatically compress that lag. It could potentially provide forecasters with a continuously updating picture of rapidly developing threats, giving them the information they need to issue warnings earlier and with greater confidence about intensity and track. The research community is genuinely excited about this potential, and that excitement is grounded in real demonstrated capability rather than speculation. But here is where the story develops a complication that the AI weather prediction community is actively and honestly grappling with, because the scientists involved are careful people who understand the limits of their own systems. These AI models learn from historical data. That is their mechanism. That is both the source of their impressive performance and the boundary of their reliability. They are pattern matching engines of extraordinary sophistication, but everything they know about how the atmosphere behaves, every statistical relationship they have internalized, every learned association between an atmospheric configuration and its subsequent evolution comes from observations of an atmosphere that existed in the past. When the AI model sees a particular arrangement of temperature, moisture, pressure, and wind, it asks, what happened next? The last time the atmosphere looked like this. The problem is that the atmosphere may be moving into configurations that don't have strong historical analogues. Cape values of 3,500 joules per kilogram in early March over Michigan were not common historical occurrences. Gulf moisture reaching that far north that early in the year was anomalous by historical standards. The loaded gun setup that produced the Union City tornado was operating at the outer edge of, or potentially beyond, the range of conditions well represented in the training data. For a physics-based model, this is manageable, because the physics apply regardless of whether the specific configuration has been seen before. For a pattern matching model, operating at the edge of or beyond the training distribution is a more fundamental challenge. The learned patterns become less reliable precisely when the conditions are most unusual, which tends to be precisely when the most dangerous weather is occurring. Some researchers are pursuing hybrid architectures that attempt to combine the best properties of both approaches. Systems like neural GCM embed machine learning components within a framework that preserves the physical constraints of the traditional equations. The physical laws act as guardrails, ensuring the model cannot produce solutions that violate conservation of energy or momentum regardless of what the learned components suggest, while the machine learning components provide efficiency and pattern recognition capabilities that the pure physics simulation lacks. These hybrid systems may ultimately prove more robust in unprecedented atmospheric environments than either pure AI or pure numerical models alone. The goal toward which the entire field is collectively and with some urgency working as a forecasting system capable not only of matching historical accuracy benchmarks, but of maintaining and improving that accuracy as the atmosphere evolves into territory the historical record does not fully represent. A system that can be continuously retrained on new observations as the climate shifts, that can recognize when it is operating at the edges of its training distribution and communicate that uncertainty appropriately, and that can do all of this fast enough to compress the warning gap that cost people their lives in Michigan. Whether that goal is achievable and on what timeline is one of the most consequential open questions in applied atmospheric science right now. Because the next outbreak isn't waiting for the technology to be ready, and the one after that isn't either. Part 12. The growing mystery of rapidly intensifying storm systems. There is a pattern appearing in storm data across multiple categories of severe weather that atmospheric scientists are increasingly focused on, and that the public has not yet fully absorbed. It is not subtle in the data. It is not a statistical whisper that requires careful squinting at a regression line to perceive. It is a pattern significant enough that operational forecasters across multiple disciplines, hurricane specialists, tornado researchers, winter storm analysts, are all independently encountering versions of the same problem and arriving at versions of the same uncomfortable conclusion. Storms of many different kinds are intensifying more rapidly than historical patterns would predict. Not just slightly more rapidly, in some cases dramatically more rapidly, at rates that catch forecasters off guard, compress warning timelines to near zero, and leave communities with almost no time to respond before the full force of a system arrives. To understand why this matters so much, you need to appreciate what warning time actually represents in the context of human survival. Every minute of advance warning before a violent tornado or a major hurricane makes landfall translates in the aggregate into lives saved. Emergency managers use warning time to issue evacuation orders. Families use it to move to shelter. Hospitals use it to prepare. Emergency responders use it to pre-position resources. The entire architecture of emergency management in the United States is built on the assumption that dangerous weather systems will develop and intensify on timescales that allow at least some meaningful preparation window. When storms intensify faster than the models predict, that assumption fails. The preparation window collapses, and the gap between what people were told to expect and what actually arrives can be lethal. In the hurricane context, rapid intensification has become one of the defining and deeply concerning features of recent Atlantic and Gulf seasons. The technical definition of rapid intensification is specific: an increase in maximum sustained wind speed of 35 miles per hour or more within a 24-hour period. That threshold was established because it represents a rate of strengthening that was historically unusual, something that occurred under specific and recognizable conditions, primarily over anomalously warm sea surface temperatures, with low atmospheric wind shear limiting disruption to the developing storm structure. It was a threshold that, when crossed, warranted special attention precisely because of its rarity. It is not rare anymore. Rapid intensification has occurred with enough frequency in recent Atlantic and Gulf seasons that it has transitioned from an exceptional footnote in hurricane forecast discussions to a standard consideration, something forecasters now explicitly account for in their probabilistic intensity guidance, rather than treating as an outlier scenario. The National Hurricane Center has expanded its rapid intensification guidance products in direct response to the increased frequency of the phenomenon. That operational change, driven by operational necessity, is itself a form of institutional acknowledgement that the baseline has shifted. Hurricane Otis, which struck the Mexican Pacific coast near Acapulco in October 2023, remains the most dramatic recent illustration of what rapid intensification looks like at its most extreme and most deadly. Otis intensified from a tropical storm with winds around 70 miles per hour to a Category 5 hurricane with winds near 165 miles per hour in approximately 12 hours. 12 hours. That is not a storm that intensified rapidly. That is a storm that transformed from a moderate tropical threat into one of the strongest landfalling Pacific hurricanes ever recorded within a single news cycle. The forecast models failed to capture the intensification until the storm was already approaching peak strength. The communities in Acapulco and the surrounding region had preparation windows measured in hours, not days. The death toll reflected that compressed timeline directly and tragically. The mechanisms behind Otis's extraordinary intensification are still being studied, but the primary factors identified include exceptionally warm sea surface temperatures in the eastern Pacific providing an unusually rich energy source, a favourable upper-level wind environment with low shear allowing the storm's structure to organise without disruption, and a moist atmospheric column that supported efficient convective development around the storm's core. Each of these factors individually would have supported intensification. Their simultaneous presence created conditions for intensification at a rate that exceeded the model's ability to project. The parallels to the Michigan tornado situation are instructive, even though tornadoes and hurricanes are categorically different phenomena operating at vastly different spatial and temporal scales. A hurricane is a synoptic scale system hundreds of miles across that may persist for days or weeks. A tornado is a mesoscale phenomenon perhaps a few hundred meters wide that may last minutes to an hour. Comparing them directly is like comparing a wildfire to a blowtorch. The scales are incomparable, but the underlying dynamic driving both toward this pattern of unexpected rapid intensification shares important similarities that researchers are beginning to examine as a connected phenomenon rather than two separate disciplinary problems. In both cases, atmospheric energy is building faster than historical patterns would suggest it should. In both cases, that energy is releasing in storms that intensify more rapidly than the models project. And in both cases, the result is severe weather arriving with less warning than the systems built to protect people can provide. The warning gap that opened up in Michigan on the night of March 5th is a mesoscale version of the warning gap that opened up along the Acapulco coast in October 2023. The physics are different, the scale is different. The outcome, communities struck by weather more intense than they were warned to expect, with less time to prepare than the system promised them, is the same. In the tornado context specifically, the phenomenon that creates the Michigan-type warning failure is what researchers call rapid supercell development. Under normal severe weather conditions, the transition from ordinary convection, the kind of disorganized thunderstorm activity that produces heavy rain and perhaps small hail, to organized supercell capable of producing a violent tornado, is a process that takes time and that leaves observable signatures in radar data that experienced forecasters can recognize and respond to. The developing rotation becomes visible. The storm's structure organizes in ways that the warning system is designed to detect. There is, in most cases, a window between the moment forecasters can see what is developing and the moment it becomes dangerous. When instability is sufficiently high and wind shear is in precisely the right configuration, that transition can happen with a speed that eliminates the window almost entirely. A cluster of disorganized convective cells can consolidate into a supercell with a persistent rotating mesocyclone in a time frame short enough that the radar update cycle, the time between successive radar scans, is too slow to provide forecasters with adequate lead time. The storm is ordinary convection on one scan and a rotating supercell producing a violent tornado on the next. The warning that should have preceded the tornado is being written as the tornado is already on the ground. Researchers studying rapid intensification across weather system types are searching for common mechanisms that might explain why this pattern is appearing simultaneously in phenomena as different as Gulf hurricanes and Michigan supercells. Warmer sea and land surface temperatures providing additional sensible and latent heat energy to developing systems are one consistently identified factor. Changes in atmospheric wind patterns, particularly in the configuration of the jet stream, and the upper-level flow that determines the shear environment for developing convection, are another. A jet stream that is more variable, that dips and amplifies more dramatically than it historically did, can create environments where the wind shear profile shifts rapidly from unfavourable to ideally favourable for supercell development in very short time periods, contributing to the sudden onset character of some tornado outbreaks. Some researchers are examining a more subtle factor involving the vertical distribution of atmospheric moisture. Historical observations of water vapor in the atmosphere show characteristic profiles, the way moisture content typically decreases with altitude under various synoptic conditions. There is emerging evidence that these profiles are changing, with more water vapor available at certain altitude ranges than historical records suggest was typical. Changes in moisture distribution at different levels of the atmosphere affect the energetics of convective development in ways that are still being quantified, but that may contribute to faster rates of convective organization and intensification under favorable conditions. The honest and complete scientific answer to the question of why storms are intensifying faster is that the full mechanism, the integrated explanation that ties together all the contributing factors into a coherent and quantitatively predictive framework, is not yet assembled. The observation is unambiguous. The data across hurricane records, tornado outbreak analyses, and severe convective event databases consistently shows the same directional signal. Storms are intensifying faster, the timelines are compressing, the warning gaps are growing. That much the science has established with confidence. The explanation is still being constructed piece by careful piece in research institutions and field campaigns and model validation studies that will eventually produce the integrated understanding needed to actually solve the forecasting problem. Science works at the pace of rigor, which is the right pace, except that it feels agonizingly slow when the storms are not waiting for the papers to be published. And in the meantime, events like the Michigan outbreak and Hurricane Otis, and the outbreaks before them and the ones that will come after, keep arriving as data points in a data set that nobody wants to be collecting, but that everybody knows is telling them something important. The question is whether we can decode the message before the next storm writes another line. Part 13. Solar activity in the atmosphere. The Sun operates on a cycle. It has been doing this for as long as the Sun has existed, which is approximately 4.5 billion years, so it has had considerable time to develop the habit. Every 11 years, roughly speaking, solar activity rises from a quiet minimum to an energetic maximum and back again, driven by the complex interplay of magnetic fields threading through the solar interior and erupting at the surface in patterns that scientists have been observing, documenting, and attempting to fully understand for centuries. At solar maximum, the Sun is, in the most literal sense, angrier. It produces more solar flares, which are intense bursts of electromagnetic radiation, released when magnetic field lines in the solar atmosphere reconnect explosively. It generates more coronal mass ejections, which are enormous clouds of magnetized plasma hurled outward through the solar system at millions of miles per hour. And it intensifies the solar wind, the continuous stream of charged particles flowing outward from the Sun's corona that bathes every planet in the solar system in a perpetual invisible gale of radiation. At solar minimum, the Sun quiets. Flares become infrequent. Coronal mass ejections are rare. The solar wind slackens. The Sun still burns with the same fundamental ferocity, converting 600 million tons of hydrogen into helium every second through nuclear fusion at its core, but the surface activity that makes solar maximum such a dynamic and occasionally disruptive phenomenon fades to a relative calm. The cycle has been observed and recorded since the 17th century, when astronomers first began systematically tracking sunspot numbers as a proxy for solar activity levels. Sunspots are regions of intense magnetic activity on the solar surface that appear darker than their surroundings because the magnetic field suppresses convective heat transport, making them cooler and therefore less luminous than the surrounding photosphere. More sunspots mean higher solar activity. The historical sunspot record, painstakingly assembled from observations made at observatories around the world across more than 3 centuries, gives us a remarkably detailed picture of how solar activity has varied across dozens of complete cycles. That cycle influences Earth in ways that range from the spectacular to the deeply practical. At solar maximum, the increased frequency of coronal mass ejections means more geomagnetic storms, which are disruptions to Earth's magnetic field caused by the interaction between the solar wind and the magnetosphere. Geomagnetic storms can induce electrical currents in long conductors at Earth's surface, potentially damaging power grid infrastructure. They disrupt satellite communications and GPS accuracy. They increase radiation exposure for astronauts and for passengers on high-latitude airline routes, and they produce the auroral displays, the northern and southern lights, that paint the night sky in green and purple curtains of light at high latitudes and during particularly intense geomagnetic storms at latitudes as far south as the continental United States. Solar maximum for the current cycle, designated Solar Cycle 25 by the International Numbering Convention, occurred approximately around 2025 to 2026. Solar Cycle 25 has been notably active, with sunspot numbers and flare frequencies exceeding the predictions that solar physicists made at the cycle's outset in 2019, when many researchers expected it to be a relatively modest cycle. Instead, it has been vigorous, producing multiple significant geomagnetic storms, widespread auroral displays visible at unusually low latitudes, and at least one solar flare among the most powerful recorded in recent decades. That timing, solar maximum coinciding with the period of the Michigan tornado outbreak, and the broader pattern of anomalous severe weather activity in early 2026, has not escaped the attention of researchers who study potential connections between solar activity and Earth's atmospheric behaviour. And this is where the discussion requires careful navigation, because the scientific territory here ranges from well-established physics to genuinely contested hypothesis, and conflating the two does a disservice to both. The connection between solar variability and Earth's weather is one of the more actively debated areas at the intersection of solar physics and atmospheric science. Intellectual honesty requires representing that debate accurately and without sensationalizing the uncertainty in either direction. The dominant drivers of Earth's climate system are, by scientific consensus, internal to the Earth-atmosphere-ocean system. Greenhouse gas concentrations in the atmosphere, sea surface temperatures, land surface characteristics including ice cover and vegetation, and episodic volcanic activity that injects aerosols into the stratosphere are the primary forcings that drive both long-term climate variability and shorter-term weather pattern anomalies. These are well-quantified, physically understood mechanisms with strong empirical support. The total variation in solar energy output between solar minimum and solar maximum is small. Measurements from satellites above Earth's atmosphere have established that the difference in total solar irradiance between the quiet sun and the active sun is approximately 0.1%. Mainstream climate science, supported by multiple independent lines of evidence, holds that this variation in total energy output is insufficient on its own to produce significant global surface temperature changes or to drive the kind of atmospheric circulation anomalies that would be required to influence severe weather frequency and intensity at the level that would be detectable against the background noise of natural variability. However, the total energy story is not the complete story, and some researchers have identified potential pathways by which solar activity might influence atmospheric circulation patterns through mechanisms that do not depend on changes in total solar energy output. These proposed mechanisms are more subtle, more indirect, and considerably more contested, but they are taken seriously enough by a subset of the research community to merit careful examination rather than dismissal. The first proposed pathway involves solar ultraviolet radiation specifically, rather than total solar output. Ultraviolet radiation varies much more dramatically than total irradiance across the solar cycle, with changes of several percent rather than fractions of a percent between minimum and maximum. This matters because ultraviolet radiation is absorbed primarily by ozone in the stratosphere, the layer of atmosphere sitting between roughly 10 and 50 kilometers above Earth's surface. When solar ultraviolet flux increases at solar maximum, it increases the rate of ozone photochemistry in the stratosphere, altering the stratospheric temperature structure. A warmer stratosphere changes the temperature gradient between the stratosphere and the troposphere below it, and that gradient influences the behavior of the stratospheric polar vortex, the large-scale circulation pattern that confines cold polar air to high latitudes during winter. The polar vortex, when it is strong and stable, keeps Arctic air locked over the poles and maintains a relatively stable jet stream pattern at mid-latitudes. When it weakens or becomes disrupted, it can allow cold polar air to plunge southward while simultaneously pushing the jet stream into more amplified, wavy patterns that create persistent weather anomalies across large regions. Some researchers have proposed that the solar ultraviolet influence on stratospheric temperatures provides a top-down pathway by which solar cycle variability could modulate polar vortex behavior and, through it, surface weather patterns at mid-latitudes. The proposed effect is subtle, operating over seasonal to annual timescales, and its detection in observational data requires careful statistical analysis to separate from the much larger natural variability of the climate system. The second proposed pathway is more exotic and considerably more controversial. It involves cosmic rays, which are high-energy charged particles originating from sources outside the solar system, primarily supernova remnants and other energetic astrophysical objects that continuously bombard Earth's atmosphere from all directions. The solar wind and the sun's magnetic field partially shield Earth from cosmic rays, and this shielding is more effective at solar maximum when the solar wind is stronger and the sun's magnetic field is more extended. At solar minimum, when the solar wind weakens, more cosmic rays penetrate to the lower atmosphere. A hypothesis proposed by Danish physicist Henrik Svensmark in the 1990s suggested that cosmic rays influence cloud formation in the lower atmosphere by ionizing air molecules, creating charged clusters that can serve as nuclei around which water droplets condense to form clouds. If cosmic ray flux increases at solar minimum and decreases at solar maximum, and if that flux change affects low cloud cover, then the solar cycle might influence Earth's radiation balance and atmospheric circulation through this indirect astrophysical pathway. The hypothesis generated significant research attention and some experimental support from laboratory studies, including experiments conducted at the CERN Particle Physics Laboratory in Switzerland that confirmed cosmic rays can enhance aerosol nucleation under controlled conditions. The broader atmospheric significance of this effect, whether the laboratory-scale process translates into cloud cover, changes large enough to affect surface weather patterns at the global scale, remains genuinely unresolved. Observational studies looking for correlations between cosmic ray flux and cloud cover in satellite data have produced mixed results, with some studies finding suggestive correlations and others finding no statistically significant relationship. The scientific community has not converged on a consensus that this mechanism operates with sufficient strength to be a meaningful driver of weather variability. The March 2026 tornado outbreak occurred near solar maximum, and the straightforward atmospheric explanation for it, anomalous Gulf moisture, exceptional Cape values, strong wind shear, a loaded gun atmospheric setup that released explosively, does not require a solar connection to be complete and physically coherent. Correlation is not causation, and the history of atmospheric science contains cautionary examples of compelling seeming correlations between solar activity and weather phenomena that did not survive rigorous statistical scrutiny. What the solar maximum context genuinely provides, stripped of any overreach in either direction, is a reminder of something important. Earth's atmosphere is not a closed system. It does not operate in isolation from its cosmic environment. It is embedded within the heliosphere, the vast bubble of solar influence extending billions of miles into space, and it is continuously receiving inputs from that environment in the form of radiation, charged particles, and magnetic field variations that originate 93 million miles away at the surface of a star. The full accounting of what drives atmospheric behavior, from the largest planetary circulation patterns down to the convective trigger that fired the Union City supercell, is more complex than any current model fully captures. The humility to acknowledge the edges of current understanding is not a weakness in the scientific enterprise. It is the prerequisite for the kind of careful, rigorous work that eventually fills in what we do not yet know. The Sun has been running its 11-year cycle for 4.5 billion years. We have been watching it carefully for about 300. The ratio of what we know to what remains to be understood should give everyone, scientists and non-scientists alike, a certain appropriate pause before claiming the picture is complete. Because the atmosphere, as March 2026 reminded us rather forcefully, is still capable of surprising us, and it may be getting better at it. Part 14. Extreme weather is appearing earlier in the year. There is a metric that atmospheric scientists have been quietly tracking for years that the general public has not fully absorbed, and the March 2026 Michigan tornado is one of the most dramatic data points it has produced. It does not have a catchy name. It does not generate the kind of headlines that a record-breaking hurricane or a historic wildfire produces. It is, on the surface, a fairly mundane observation about calendars and dates. But underneath that mundane surface, it carries implications for public safety, emergency preparedness, and the fundamental assumptions underlying how American communities organize their relationship with severe weather risk. The calendar is shifting. The dates on which extreme weather events occur are moving, and they are moving in a consistent, measurable, and accelerating direction. To appreciate what this means in practice, consider how deeply seasonal the American experience of severe weather has historically been. Tornado season, hurricane season, wildfire season. These are not just meteorological classifications, they are cultural institutions. They organise the rhythms of emergency management agencies, which staff up and prepare differently at different times of year. They organise the behaviour of communities in risk zones, which are more collectively vigilant during the acknowledged danger period and less so outside it. They organise the safety protocols of schools, outdoor venues, summer camps, agricultural operations, and countless other institutions that make explicit or implicit decisions about risk based on the time of year. The entire infrastructure of severe weather preparedness in the United States, from the physical infrastructure of shelter systems to the psychological infrastructure of public awareness, is calibrated to a seasonal model that the atmosphere appears to be in the process of revising. Tornado climatologists have documented a trend that has been accumulating in the data for decades, but has only recently become visible enough at the aggregate level to generate serious research attention. The average date of the first significant tornado outbreak of the year in the United States has been trending earlier over recent decades. Outbreaks that were historically associated with the mid to late April transition into peak severe weather season are now occurring in late March, with increasing frequency, and in some years, in early March. The southern tier of the United States has long experienced active late winter severe weather, and February tornado outbreaks are not unprecedented in the historical record for states like Alabama, Mississippi, and Arkansas. The Deep South sits close enough to the Gulf moisture source and at low enough latitudes that early season instability has always been possible there. What is changing is not the existence of early season events in the traditional risk zones, but their intensity, their geographic reach, and their intrusion into states and latitudes that were historically insulated from significant tornado risk until much later in the calendar year. An EF3 tornado in Michigan in early March is not simply an early season event in a state with established tornado history. It is a violent, historically anomalous tornado in a state with very limited exposure to storms of that intensity, arriving at a calendar date that sits well outside even the loosest definition of Michigan's historical severe weather window. It is the seasonal boundary moving visibly and consequentially into new territory. The phenomenon extends well beyond tornadoes, and the consistency of the signal across different categories of extreme weather is part of what makes it scientifically compelling, rather than a statistical artifact of any single dataset. Heat waves have been arriving earlier in the summer season and persisting later into autumn across multiple regions of the Northern Hemisphere. The period during which dangerously high temperatures are possible has lengthened at both ends, with the first significant heat events of the year arriving earlier in June and the last significant events persisting later into September and October than historical records from the mid-20th century would have predicted. Wildfire seasons across the western United States and Canada provide some of the most visually dramatic evidence of the seasonal expansion phenomenon. The concept of a discrete fire season, a bounded period of elevated fire risk bookended by wetter, cooler conditions that naturally suppress fire spread, has been dissolving in real time across much of the American West. Fire behaviour analysts and forest managers have been documenting for years that the window during which large fire conditions exist, low humidity, high temperatures, dry fuels, and critical fire weather, has been extending progressively at both its spring and autumn boundaries. Fires that were historically limited to the late summer and early autumn peak are now occurring in May and June on one end, and persisting into November and December on the other. Some researchers studying Western fire climatology have essentially abandoned the concept of a fire season entirely in favour of a fire year, acknowledging that the bounded seasonal model no longer accurately describes the risk landscape. Hurricane season provides another dimension of the same pattern. The Atlantic hurricane season is officially defined as running from June 1st through November 30th, a window established based on historical frequency distributions of tropical storm and hurricane activity. But named storms have been appearing with increasing frequency outside those official boundaries in late May and in December, at sufficient rates that the National Hurricane Center has adjusted its tropical weather monitoring protocols to begin issuing advisories earlier in the calendar year The effective endpoints of meaningful hurricane risk have shifted outward, even if the official season dates remain anchored to their historical positions for institutional continuity. The mechanism driving this consistent cross-category pattern of seasonal boundary expansion is closely tied to the thermodynamics of a warming atmosphere, and the physics are relatively straightforward even if the full implications are still being quantified. Most categories of extreme weather require specific atmospheric conditions to occur. Severe convection and tornado production require CAPE values above certain thresholds, moisture at specific depths, and wind shear in particular configurations. Heat waves require blocking high-pressure systems to persist over sufficient timescales to drive temperatures above critical thresholds. Wildfires require the combination of low fuel moisture, low atmospheric humidity, high temperatures, and often strong winds to spread. Tropical cyclones require sea surface temperatures above roughly 26 degrees Celsius to sustain organised convection. In a warming atmosphere, all of these threshold conditions are achieved earlier in the calendar year as the seasonal warming progresses, and they persist later into the year as the seasonal cooling proceeds. The warming effectively compresses the cold, threshold-limited periods at both ends of the year and expands the warm, threshold-permissive period in the middle. The window during which the atmospheric ingredients required for any given category of extreme weather are simultaneously available is wider than it was. Not dramatically wider in any single year, but consistently wider across the trend, accumulating into a measurable and consequential shift over decades. For tornadoes specifically, the early season extension of risk carries dangers that go beyond the purely meteorological. The cultural infrastructure of tornado preparedness, the habits, awareness, and reflexive responses that develop in communities with long experience of tornado risk, is calibrated to the traditional season in ways that are deeply embedded and slow to change. People who live in tornado-prone areas have internalized, over years of experience and community culture, a heightened alertness that activates in April and May and gradually relaxes as summer progresses. Parents remind children about shelter procedures at the start of tornado season. Schools conduct tornado drills in the spring. Emergency managers increase their monitoring intensity. Storm spotter networks activate. The entire community apparatus of tornado awareness shifts into a higher gear when the calendar says it's time. In March, that gear has not yet engaged. The psychological seasonal model says it is still winter, still transitional, still the period between the last cold snap and the first warm weekend of spring. The idea that a violent EF3 tornado could arrive in this in-between period, in a state with no strong cultural memory of violent tornadoes, runs against deeply held intuitive expectations about how and when dangerous weather behaves. And intuitive expectations, even wrong ones, govern behaviour in the critical seconds and minutes when the sirens go off and a person has to decide whether to move immediately or to step outside and look at the sky first. When a violent EF3 tornado arrives in early March in a state with limited tornado history, it finds a population that is not psychologically primed for this particular threat. The sirens sound, and some percentage of people will hesitate, not because they are careless or uninformed, but because at some level, in the part of the brain that runs on pattern recognition and seasonal intuition rather than rational meteorological analysis, they did not believe this was possible. Not here, not in Michigan, not in March. The hesitation is understandable, it is human, and it costs time that, in an EF3 tornado, is measured in the distance between you and a basement. That moment of hesitation is measured in lives, not metaphorically, literally. Tornado fatality research has consistently found that the people most likely to be killed in tornado events are those who do not take shelter promptly, and the reasons people do not take shelter promptly include not just inadequate warning time but inadequate psychological preparation, the absence of the ingrained seasonal alertness that prompts immediate action rather than the few seconds of hesitation that can be the difference between a basement and a collapsing wall. The expansion of the extreme weather season is not a hypothesis awaiting confirmation. It is an observation recorded in multiple independent datasets across multiple categories of weather events, consistent in its directional signal across different methodological approaches and different research groups analysing different phenomena. The atmosphere is spending more of the year in a state of elevated energy. The boundaries of when and where that energy releases as extreme events are expanding at both ends of the calendar, and the communities, the emergency management systems, The building codes, the cultural habits of preparedness, and the psychological seasonal models that govern how people respond when the sirens go off are all calibrated to a past that is becoming less and less like the present. Which brings us back finally to where this story began, to a neighbourhood in southern Michigan on the night of March 5th, 2026, to an EF3 tornado that wasn't in the forecast and wasn't supposed to be there, and to the question that has been sitting underneath everything we have discussed, waiting for its moment. Part 15. The questions scientists can't yet answer. We began with a single night, March 5th into the 7th, 2026, an EF3 tornado over Branch County, St. Joseph County, and Cass County in southern Michigan. Winds between 145 and 170 miles per hour. 8 deaths across the broader outbreak. 4 of them in Michigan alone. More than 30 injuries, many of them people pulled from the wreckage of homes they had lived in for years, in some cases for decades. 100,000 customers without power across multiple states. A high school gymnasium converted overnight from a place where teenagers play basketball into a coordinated emergency relief operation. And underneath all of it, underneath the debris fields and the damage surveys and the fatality counts, a question that nobody standing in that wreckage could immediately answer with confidence. Why here? Why now? Why this strong, this early in the year, in a place that almost never sees anything like this? We have spent considerable time assembling the pieces of an answer, moving from the specific wreckage of Union City outward, through the atmospheric mechanics that produced the storm, through the forecast failure that left communities without adequate warning, through the long-term patterns of geographic and seasonal shift that placed this event in a broader and more troubling context. The honest accounting of where that assembly effort has left us is this. We have most of the pieces, but not all of them, and the ones we're still missing are not peripheral details. They are central to the most important question the Michigan tornado raises. The atmospheric mechanics of the event itself are, in retrospect, reasonably clear. An anomalous moisture surge from the Gulf of Mexico arrived over the Great Lakes region weeks earlier than historical patterns would predict for early March. Convective available potential energy values in the affected region reached levels near 3,500 joules per kilogram, numbers more typical of the height of tornado season in May than of the early spring transition. Strong directional winds shear through the atmospheric column provided the rotational conditions necessary for supercell thunderstorm development. A convective inhibition cap trapped the accumulated heat and moisture beneath it, while the energy continued to build, holding the atmosphere in a state of loaded tension until the trigger arrived and the release was explosive. The storm that resulted from this alignment had every atmospheric ingredient it needed to produce a violent long-track tornado, and it did. The forecast failure is also reasonably well understood in retrospect, which is simultaneously reassuring in that it is explicable and deeply uncomfortable in that the explanation does not suggest an easy fix. Mesoscale convective processes, the small-scale atmospheric features that served as the initiating triggers for rapid storm development, developed faster than the operational forecast models could capture at their current grid resolution. The models were working at spatial scales that rendered the critical initiating features effectively invisible until the storm development was already underway and the warning-led time had collapsed to minutes. This is a known limitation of numerical weather prediction, a limitation the research community has been aware of and working to address for years. It is a limitation that the Michigan atmospheric environment, with its anomalously high instability and rapidly evolving mesoscale structure, tested at precisely the worst possible moment. The geographic anomaly, the central fact that this storm happened in Michigan rather than in Oklahoma or Kansas, where a tornado of this intensity would be historically expected, fits into a pattern of documented eastward and northward shift in tornado activity that multiple independent research groups working with different data sets and different methodologies have identified over recent decades. The proposed mechanism for that shift involves a combination of changing large-scale atmospheric circulation patterns, warmer Gulf of Mexico sea surface temperatures extending the geographic reach of moisture transport, and altered jet stream behavior that collectively expand the geographic zone, where the maximum ingredients for severe weather come together. The Michigan tornado is not inexplicable within this framework. It is, in fact, almost exactly what the framework would predict as the expanding risk zone encounters a historically low-risk region, but here is precisely where the honest scientific answer reaches its own edge and acknowledges what it does not yet know with the certainty the question deserves. We cannot state with scientific confidence that the Union City tornado was a direct, attributable consequence of the systematic atmospheric changes described in the research literature on tornado climatology and severe weather trends. The atmosphere is a chaotic system in the precise mathematical sense of that term, meaning that small differences in initial conditions can produce dramatically different outcomes, and that even in a statistically stable climate, the distribution of possible events includes rare extremes at the tail. An EF3 tornado in Michigan in early March is historically unusual. It is not, strictly speaking, physically impossible under atmospheric conditions that could have occurred even without any systematic change in the climate background state. The event might represent the tail of a distribution that has always existed, observed now because detection technology and reporting networks are more comprehensive than they were in earlier decades, rather than because the distribution itself has shifted. This is the crux of a genuine scientific debate, and it deserves to be represented accurately rather than flattened into a false certainty in either direction. The debate is conducted by careful, rigorous scientists who disagree in good faith about the relative contributions of natural atmospheric variability and systematic climate-driven change to the increasing frequency and intensity of severe weather events in historically low-risk regions. It is not a debate between scientists who take the threat seriously and scientists who dismiss it. Both sides of the debate take it seriously. They disagree about the quantitative attribution, about how much of the observed signal represents a genuine shift in the underlying distribution, and how much represents sampling variability in a distribution that has always had a long tail. The evidence, taken as a whole, points toward a genuine atmospheric shift. The geographic signal in the tornado occurrence data is consistent across multiple independent analyses. The seasonal signal, the earlier arrival of severe weather season and the increased intensity of early season events, is documented across multiple categories of extreme weather. The atmospheric mechanisms, warmer Gulf waters, changing jet stream behavior, expanded moisture transport, are physically coherent and observationally supported. The magnitude and pace of the shift are still being quantified with the precision that would be needed for confident attribution of individual events. But the directional signal, the consistent pointing of the evidence toward an atmosphere that is increasingly capable of delivering severe weather to places and times that were historically outside its reach, is not seriously contested among the researchers who study it most carefully. The uncertainty is not an excuse for inaction, and it should not be interpreted as one. Uncertainty about the precise magnitude of a risk does not reduce the obligation to prepare for it. We do not know exactly how much the severe weather risk in Michigan has increased. We know it has increased enough to kill 4 people in an early March tornado that the forecast system failed to adequately predict. That knowledge is sufficient to drive action on the preparedness dimensions of this problem that do not require resolving the attribution debate to be worth pursuing. What the March 2026 outbreak demonstrated, regardless of where the attribution question ultimately lands, is that the foundational assumptions underlying American tornado preparedness are overdue for comprehensive revision. The geographic boundaries of serious tornado risk have expanded beyond the map that emergency management infrastructure was built around. The calendar boundaries of tornado season have shifted earlier in ways that the cultural habits and institutional protocols of preparedness have not kept pace with. The warning systems have exploitable limits that the atmospheric environment is increasingly testing. The housing stock in the newly at-risk regions was designed and built to a risk profile that no longer accurately describes what those communities face. And the cultural habits of tornado preparedness, the ingrained reflexes and seasonal vigilance that develop only through years of community experience with the threat, have not yet had time to develop in the communities that now need them most urgently. A second, potentially more dangerous storm system was already assembling as rescue workers were still picking through the Michigan debris. 36 million people sat within its projected severe weather risk zone. The atmosphere was loading again, precisely as the communities targeted by the first outbreak were still in the acute phase of their emergency response, before the power was fully restored, before the injured were all out of the hospital, before the families of the dead had finished making the phone calls that nobody wants to make. The question of whether the warning systems would perform better for the second outbreak than they had for the first was entirely unresolved. The limitations that produced the near-zero lead time for the Union City tornado had not been fixed. They could not be fixed in the days between one outbreak and the next. They are structural limitations that will take years of scientific development and institutional investment to meaningfully address. The Earth's atmosphere has never been static. This is worth stating clearly, because the science of paleoclimatology has made it abundantly clear that the atmospheric conditions humans have experienced across recorded history represent a narrow slice of the full range of configurations the atmosphere has occupied across geological time. Ice ages buried the northern continents under kilometers of glacial ice. Warm periods produced forests at latitudes that are now tundra. Atmospheric carbon dioxide concentrations have varied by factors of 10 or more across deep time, driving surface temperatures and circulation patterns into configurations that would be entirely unrecognizable to anyone alive today. Change is the atmosphere's natural condition. Stability is the exception, not the rule. What is specifically concerning about the current moment is not that the atmosphere is changing. It is that the pace of change appears to be accelerating in ways that our institutions, our infrastructure, our forecasting systems, and our built environment were not designed to accommodate. Buildings last for decades. Building codes change slowly. Cultural habits of preparedness take generations to develop. Forecasting systems require years of research, validation, and operational deployment to improve meaningfully. The atmosphere is not operating on any of those timescales. It is updating faster than the systems built to respond to it can follow. The Michigan tornado was either an isolated extreme event sitting at the tail of a distribution that has always existed, an unusually bad night in a state that occasionally has unusually bad nights, with no particular implication for the future beyond the grief and rebuilding it demands. Or it was a preview, a demonstration of what an atmosphere that has expanded its geographic reach and its seasonal window can now deliver to communities that were not on the historical list and have not yet been added to the preparedness infrastructure that protects the communities that were. Scientists are not yet in a position to tell you with certainty which interpretation is correct. They will say that directly if you ask them, and they deserve credit for that honesty in a public discourse that often rewards false certainty over accurate uncertainty. But here is what the same scientists will tell you. More quietly, in the conversations that happen after the formal presentations are over and the cameras are off. The evidence is trending toward preview. The trend lines across the datasets they study are consistent in their direction. The atmospheric ingredients that made March 5th possible in Michigan are becoming more available across more of the calendar year and more of the geographic map, not less. And the communities that are about to find themselves on the new list, the ones that will experience their own version of the Union City night in the coming years, do not yet know that their names have been added. The question is not whether the atmosphere is changing. That question has been answered by the data, repeatedly and consistently, across multiple independent lines of evidence. The question is whether we, meaning our institutions, our infrastructure, our warning systems, our building codes, our emergency management protocols, and our collective cultural habits of preparedness, can change fast enough and comprehensively enough to keep pace with an atmosphere that is not waiting for us to catch up. And standing in the ruins of Union City, Michigan, looking at a concrete foundation slab sitting open to the March sky, where someone's house used to be, surrounded by the debris of a life that was there the night before and is scattered across a field this morning, it is very hard to feel confident about the answer.